Okay, this is going to be our third video on electromagnetic induction. In this video, we're going to be covering section 29.4, and this is all going to be on motional EMF. I'm not expecting this to be too long of a video, so we'll get right into it and see how quickly we can get through this here. Okay, so motional EMF. We can think of induced EMF in a circuit in terms of the motion of free charges, right? We know that all conductors are good conductors because they have free charge in them that can move around. So we can think of motional well, we can think of induced EMF in terms of these free charges in these conductors. Let's say we're thinking about a positive charge, right? So we have our positive charge here. Our charge is greater than 0. Then we know that the magnetic force experienced by that charge is given by this expression that we have here, right? And we're looking at this setup here. So we have a magnetic field that's going into the page. We have our positive charge sitting on our conducting rod here. And so let's say we start to move this rod to the right with some velocity here. What's going to happen with this charge here? Well, we know it's going to experience this magnetic force, right? We're going to have a V cross B, and if we have V pointing in that direction and B into the page, and this is a positive charge, we can see that it's going to experience a force upward like this, right? And so if we keep this V going, what's going to end up happening? We're going to start to accumulate a bunch of extra positive charge at the top here at A, and a bunch of extra negative charge down at the bottom at B, right? And because of this, we're going to set up an electric field, which is going to be pointing from A to B, right? It's going to point from the positive charge to the negative charge, and this is going to be a sort of build-up, as I said, of charge of positive charge at the top or at A, negative charge down by B, and we're going to have an electric field set up. Okay, so we're going to have this charge build up until we have a balance in the forces acting on these charges. We're going to have a balance between the force that these charges experience due to the electric force and the magnetic force, right? When these two, let me scroll down a little bit here, when these two quantities are equal, we have those two forces balanced, and the whole thing kind of sets up an equilibrium state here. We have a bunch of positive charge on top, a bunch of negative charge on the bottom. They're experiencing they're experiencing electric forces which are drawing them together, and magnetic forces which are pushing them apart. Everything is in balance. Okay, we can find the potential difference across this rod. So the potential difference across the rod is simply going to be L times our electric field, right? Our potential difference is nothing but our electric field per unit length, right? And so we end up with this expression here. If we take these expressions, get rid of Q, right? We can eliminate Q from both sides. This is going to be our potential difference if we multiply it by L, right? And so that's what we've done here. We have the potential difference, which is basically the potential difference from A to B, is going to be equal the potential at A minus the potential at B, which is equal to EL, which is equal to VBL, right, from this equation here. Okay. But now what happens if we take this rod and we place this rod into a slide wire generator like we've looked at before, and the rod becomes just one part of the slide wire generator? Well, it becomes the moving part of the slide wire generator, right? So we don't do anything differently here. We're now sliding V the same as we were before. We have positive charge moving this direction, but instead of the positive charge building up at A and negative charge building up at B, what happens is positive charge starts to spill out from A, right, and go around the loop and in to where we would have some negative charge here. Basically, we have the EMF that's driving the current around our loop, right? This is very similar in some ways to as though we had just cut out this chunk of the loop and stuck a battery in there, right? Basically, it's just acting like a battery. Now, granted, this battery or this battery-like object has to be in motion for it to actually be producing the EMF that we need, but we can think of it kind of like a battery, right? Although batteries wouldn't have to be moving, but it fills the same role. It gives us the EMF that we need to drive the current around the loop here. Okay, so that's basically what we have going with a slide wire generator. But this, this gives us a way to write. Well, if we look at this VAB, this potential difference that we looked at just a moment ago, is really our EMF across our slide wire generator. So this gives us a way to write our EMF here. So we have our what's called our motional EMF. This is an EMF due to the motion of this rod. Okay, and so this is our motional EMF, and it's equal to the speed of our conductor times the length of the conductor times the magnitude of the uniform magnetic field. Okay, and so this expression corresponds to a force per unit charge with a magnitude of VB acting over a distance of the rod, right? Acting over the distance of the rod L. Okay, so this is our force per unit charge acting over the length of the rod L. Okay. If the total resistance of the circuit is R, right? Like if the resistance of the full circuit, the rod plus the U-shaped part of the circuit is R, then we can get our current from this expression here, right? We know that VBL is actually equal to VAB, but we know that VAB is actually equal to IR. We could isolate R and solve for our current. This is the same result that we found using Faraday's law a couple of sections back. Okay. Now we could take this expression and we could make it more general, right? In this case, we're just talking about a slide wire generator with a simple rod moving perpendicular to our magnetic field and moving perpendicular to the length of the rod. But we could do this for a much more general case here. Okay, so we can generalize this motional EMF concept for any conductor of any shape moving in any time-independent, although not necessarily uniform, magnetic field. So what do I mean by that? When we're talking about things changing in space or in time, if we mean for something to be uniform, what we mean by uniform is that it doesn't change in space. It's the same everywhere. If we say something is constant, it doesn't change in time, right? So for us to be able to do what we're about to do here, we need a magnetic field that is not changing in time, but it can change in space. It can be different at any point in space, but it needs to stay that way for as long as we're doing our calculation here. Okay. So if we have a magnetic field that fits these criteria, and we have some sort of a conductor in this magnetic field that we can break up into little length chunks dl, we can add up all the contributions to the EMF, these tiny little DEs, and it's going to be written sort of in this form here, right? This is going to be, each DE is going to be equal to V cross B dotted into DL. And now the textbook always writes this down with these brackets here. Now really you don't need these brackets, and why is that? Well, we don't really need these brackets because we know that the cross product here, this vector product, has to result in a vector. And then we're dotting this vector into another vector, right? And you can only dot vectors into vectors, really, and you can only take the cross product of vectors with vectors, right? And so if we didn't have these brackets here, there would be no danger of us doing B dot DL first, because if we did B dot DL, that would result in a scalar, and we can't cross a vector into a scalar, right? So we always know that the cross product has to come first. So the brackets aren't really necessary, but the book does it everywhere, so I'll do it everywhere as well. But just be aware that you really have to do the cross product first so that you end up with a vector that you can dot into another vector, because if you do the dot product first, you don't have the remaining vector to cross with the other vector, right? So anyway, so we have this tiny element of our motional EMF. If we integrate this over a closed loop, right, a closed conducting loop, we end up with the expression that we see here. Okay, so this is our motional EMF in the most general case here, where we allow our conductor to be fully submerged in this magnetic field, and it can have different velocities for different parts of the magnetic field, and it can have different magnetic fields at different points. And so we can simply integrate over all these little chunks of dl and pick up the full motional EMF. Okay, so we have a little diagram here from the textbook that illustrates what we would be doing if we wanted to do this. We can imagine that we have some conducting loop in some sort of a magnetic field. It can be different at all the different points, but it has to be constant in time. What do we do in this case? Well, we break it up into a ton of tiny little sections, right? And over each of those tiny sections, we're gonna look at that little section as a dl. We're gonna find the velocity for that tiny section. We're gonna calculate the tiny contribution from that dl to our motional EMF. So we're going to calculate dE equals this expression that we see here, which is just the expression that we had up here. We're going to do that for every single one of these tiny little dLs, and then we're just going to sum them all up. That's what this integral is telling us. This integral is saying sum up all these tiny little contributions over this closed loop. Okay. And so if you do that, you can pull out your motional EMF. Okay. This expression here, although it may not be super obvious just by looking at it, is really completely equivalent to the expression that we came up with in section 29.2. Okay, this is the expression that we saw in 29.2, which dealt with magnetic flux. Right, this is the time rate of change of our magnetic flux. The negative of that is equal to our EMF. Here we have an expression for our motional EMF written in terms of a closed loop integral here over some cross product dotted into our tiny length elements, right? And so these are totally equivalent. You're going to use different ones in different spots depending on what the problem is asking for. Sometimes it'll be easier to use one, sometimes it'll be easier to use another. It's not always clear which one you want to use, so just be careful which one you use. Sometimes it'll be easier to use different ones. Okay. We're now going to look at two quick examples and wrap this one up. So in this first example, we're looking at motional EMF in the slide wire generator that we just looked at. So we want to suppose that we have a slide wire generator with a slide wire of length 0.1 meters moving at a velocity of 2.5 meters per second and a total resistance of the loop of 0.03 ohms. And it's going to be in a magnetic field that's perpendicular to our slide wire and to its velocity, like to the velocity of that rod, right? And our magnetic field is going to have a magnitude of 0.6 Tesla, okay? So I didn't want to, I mean, the textbook originally refers back to this diagram. I didn't want to recopy the diagram because it was kind of large, but I guess in hindsight maybe I could have. So we're basically just looking at this setup. I'll kind of redraw that down here. Although the way I've rewritten the problem leaves some ambiguity. This magnetic field could point directly upward or directly downward as it does in this case. So I'll just stick with directly downward. The wording of the problem does leave that ambiguity there, so we'll just clear it up with our diagram here, okay? So we have a slide wire generator. It looks something like this. Here's our slide wire. We have some velocity. We have some magnetic field. I won't draw it everywhere. We have some length. Okay. And so the first part of the question is asking us to find the motional EMF, right? Well, we just generated an equation for motional EMF with exactly that setup in mind, right? So we have motional EMF equal to VBL. So let's write that out. We have motional EMF equal to VBL, and all the things that made this equation true before are obviously true here because it was developed in the case of a slide wire generator. So we know we can apply all this here. We're given the velocity, the magnitude of the magnetic field, and the length of the wire, so this is just a simple substitution. Okay, and this, if you do the calculation, you'll find a motional EMF of 0.15 volts. Okay. In the second part of the question, we are asked to find the induced current. Well, we can, as we said before, we can find that sort of from V equals IR, where our V here is our motional EMF, and we can just isolate I. So we're going to have I is our motional EMF over R. We're told what R is, and so I is equal to 0.15 over 0.03, which means I is equal to 5 amps. Okay, that's our induced current. And then we want to find the force acting on the rod, right? So we're going to be looking for the force that the magnetic field is sort of exerting on the rod, right? So we want to see the force that's working against this V that we have going here, right? So we know that this is going to take the form F equals IL cross B, right? This is our magnetic force. This is our magnetic field. This is the length of the rod, and this is our I that we just calculated. Okay, we know that I is going to point in the direction of L here, the way that I've drawn it, and we know that B is perpendicular to that. So this really all is going to clean up a bunch. We can see that sort of our right hand rule. If we think about our current or our length element pointing in this direction as I have it drawn, and we think about a cross product, we can see that the force is going to point in this direction, right? L cross B with the right hand rule gives us an F pointing in this direction. Okay, and so because L and B are perpendicular, this all cleans up. We can find the magnitude, which is just going to be equal to this expression here. And now we're just at the point where we can substitute in numbers. We just calculated I. We know what L is. We know what B is. And so if you clean that all up, you can find an F, which is going to be equal to 0.3 newtons. Can't read my notes here, but I'm assuming that's correct. Double check that if it's not, but that should be right. And we know that it's pointing off to the left here. I haven't set up a coordinate system, so I can't refer to it as any sort of negative I hat direction, but I guess we could, right? We could set up some coordinates like this. If this is I hat, this is J hat, then it points in the negative I hat direction, right? Something like that. Okay, so that would be our slide wire generator expression. Now for the second example, we have something a little more interesting, a little more complicated. We're going to be looking at a Faraday disc dynamo here. So this is a way we really could generate an EMF if we wanted to. So what do we have going on here? I guess I'll start out by reading the problem. So we have in figure 29.17, which we have below here, shows a conducting disc with a radius r that lies in the xy plane and rotates with a constant angular velocity omega about the z-axis. The disc is uniform, or is in a uniform and constant magnetic field that points in the z direction. We can see they've drawn it on here for us. We want to find the induced EMF between the center of the disc and the rim. So we want to find the induced EMF between, say, these 2 points here. Okay, so between the center and the rim of the disc. Okay, so just by looking at it, it kind of seems like it could be a little bit of a complicated problem, but we can sort of reason our way through it to make it not so bad. The actual calculation itself is just one simple integral. So we have the setup where we have our motional EMF is going to be happening because the disk is moving relative to the magnetic field, right? So we have this conductor, and yeah, so it's not just a wire, it's a big disk, and it's moving in relation to the magnetic field. But we can expect that, well, it is a conductor, and it's moving in relation to this magnetic field. So we're expecting some sort of motional EMF to be happening here. Okay, the different parts, although like each of these different parts of the disk are moving with a different velocity, right? So let's be careful here. This is and did they not draw this on here? Okay, so I guess this would be like our omega. Well, they have it labeled here, but this is our omega also. Okay, so you can imagine this disk is spinning around like this. So each little chunk, so if you imagine that we break up this whole path here into little chunks, each little chunk is going to be moving with a different velocity, right? So it is moving, but we have to be careful because each of these little chunks is moving with a different velocity. The closer into the center we get here, the smaller the velocity is going to be. The farther out we get, the larger the velocity is going to be, right? So we're going to have to come up with some sort of expression that we can write each of these tiny little chunks that we're going to want to integrate over in terms of the velocity at that point. Okay, so clearly we're going to have to integrate, right? Because we're dealing with a system here where each of these tiny little sections is going to have a different v. So we need to consider each v independently as we build up this sum of contributions to our motional EMF here. Okay, so if we actually look at the little segment that they drew here, we can see that if we look at v cross b, v points kind of tangent to r omega, and b points perpendicular to that. So if we do v cross b, we can see that at every point our v cross b is going to be pointing outward, radially outward, right? So I'll just make a note here. V cross b points in the r hat or radially outward direction, right? So because of that, that means our current is going to flow radially outward, right? We're going to have a motional EMF which is pointing radially outward, and so we have a current that's kind of flowing from the inside center of our disk to the outer edge. Okay, so these conducting paths, these paths are basically just straight lines from the center outward. So you can think of this as a disk built up of a ton of wires that are all kind of like running out like this. Okay. And what we're going to end up doing is we're going to integrate along one of these wires. So we're basically just taking one wire, and we're going to break that wire up into a ton of tiny little segments and integrate over each of those. When we think about it in those terms, it's not so bad, because then we can just go back to the integral that we wrote down up here, right? And these tiny, well, this is the integral, and these tiny little contributions to our motional EMF aren't going to be so bad. We just need to calculate each of these at each point. Our DL is just going to be our tiny little segments of length as we go out along the radius. We just need to find V at each of those points. We have B, and we're all set to go, right? So let's maybe try and do that here. The first thing that we're going to need, well, okay, maybe the first thing I'll just write down the expression V cross B dotted into DL, except that here, what is our DL? Well, our DL is really just dr in the r hat direction, but we don't really care about the direction of this. I mean, we kind of care about the direction, but in the end it's just going to all go away. So really our DL is just going to go to dr, okay? And we know that it's going to point outward radially, okay? We just talked about how V and B are perpendicular, right? So V cross B gave us that outward radial direction, and since V and B are perpendicular, this is just going to go to VB, right? And this is as V is perpendicular to B, okay? And then the sort of last thing we need to kind of concern ourselves with is, well, what is the velocity at each of these tiny little steps, right? Well, if we think back to maybe stuff you looked at in high school, or maybe stuff you looked at in Physics 101, what you guys would have taken in 111. So in Physics 111, you would have looked at uniform circular motion, and you know for uniform circular motion, V is equal to omega r, right? So our tangential velocity is equal to our angular velocity times our radius, right? So times whatever radius we're at. So we can kind of put all this together. We put this V cross B into here as just VB. V becomes omega r, and our DL just becomes dr. So we end up with a DE equal to omega r B dr. Okay? I'm not sure if you guys can hear the dog barking in the background. I apologize if you can, but I'll finish this off quick and then go check what's going on. And so we just have to write down our integral now, right? We just have to put this. Basically, we have E is equal to the closed loop integral around our DE, right? And so we're going to end up with E is equal to the integral along our radial line from 0 out to r, okay? From 0 out to r, just of the expression that we have here, omega r b dr. This can be simplified to omega b 0 to r dr. And if we do that integral, we end up with omega b and we're going to have an r squared over r, oh no, over 2, sorry, evaluated at 0 and r, which is going to give us an expression like this for our motional EMF. Okay, and so that is our motional EMF for this disk, basically this Faraday disk dynamo. Okay, and you could really use this dynamo if you wanted to, if you had the proper setup to drive some sort of a current through a circuit, right? Okay, so I will leave this section here, and I will see you guys in the next one.